Yeah. So I will go one by one. So I will try to address the first issue, that is regarding the calculation of force. I think it should be reaction force. So can you please open that PPT? Yeah. So next, if you can minimize it, I can change the slide. I want to go to that slide, particular slide.
Sir,
No, I'll select that slide and then you can maximize. So yeah, can you go to the slides? Next. Yeah, नीचे आइए नीचे. Yeah, you stand. Yeah, correct. Yeah. Yeah, so I will go one by one. So I have received one query regarding the calculation of force term by Niranjana. So I will try to address that. So if you see in this case, for this particular problem, we have Neumann boundary only in these two edges. Okay, so that's why when we are going to each of the elements, only across or along these two lines we are integrating those two entries, and only along those two lines this term is non-zero. All right. So next slide. So here, as you can see, in the first element, so you have rightly pointed out that f21, while calculating f21, we actually have taken qn as 1, and while integrating this term along this edge 1 2, so we have to integrate it from local node 1 to local node 2. Okay, so in that case the limit will be from y equal to 0 to y equal to 1. So that is exactly what we have written here. So we are going in the anti-clockwise direction. Okay, we are going in the anti-clockwise direction. So that's why the limit here is from 0 to 1, and that is what exactly has been done. Whereas for the next slide, so if you see for element 2, while integrating along the boundary joining local node 1 and local node 2, so there we are integrating f2 from 0 to 1. All right, so this is not correct. So in that case it should be from 1 to 0, because we have to go anti-clockwise direction. So in that case the x varies from 1 to 0. So that is what we need to change. So you can change it from 1 to 0. Okay, because we are moving along anti-clockwise direction, so that the outward normal remains outward. All right, so accordingly you modify the dimension and the value. All right, I think the method that has been explained is good enough. Okay, so then I want to move to one more query. Can you show the query in the doc file? Yeah. In assignment 9, you said that Jacobian has been calculated as negative. So actually, if you look at assignment 9, we asked for the Jacobian for that particular mapping, and the mapping has been deliberately done such that the Jacobian will come negative, because if you see in the real element or the physical element, okay, the numbering has been done clockwise, and whereas in the master element it has been done anti-clockwise. So that has been done deliberately, and in the question we have asked that you have to calculate the Jacobian for that mapping. Okay, we didn't ask you to just go ahead and calculate the Jacobian like twice of the area of the element. Okay, you have to understand that, because always we have to move in a particular direction, and just to emphasize that point we have given that problem. Okay, that's why the answer should be minus 40. Okay, and so this is a wrong step, and in order to convince you that this is a wrong step, that problem has been given. So that way you have to look at. All right, fine. So then uh, all right, so I will come to the point that Raphael has raised. All right, so uh, so if I go to that, just open a blank slide. In this presentation is okay, but just a blank one. Yeah, so I will try to address the issue raised by Raphael. So in that case, so let us take say a bar problem. Okay, and let us take one element. Okay, and say the problem has been given like this. So this end of the bar is fixed, and here we have applied a load P naught. Okay, in addition we have a distributed load, say C naught. Okay, so this is given per unit length, and there is a point load at the end, that is P naught. So we are solving a bar problem. So this is what has been discussed at the beginning of the lecture. And if you remember, the stiffness entry turned out to be if I write this directly, so EA I have phi I comma x, phi j comma x dx. So integrate 0 to L. So I am assuming that the length of the bar is L. So if I follow that, I can find out the stiffness entry. So in that case, the stiffness matrix I will calculate. Alright, and similarly the force entry in the right hand side that we obtained from the weak form, that will appear as, in this case, a distributed load is say Fx. Okay, and then we will have phi I dx. Fine, and then we will have the Neumann boundary condition, say EAU prime at this, and then we will be having phi I 0 and L. So this is the right hand side. So this part I am not explaining because this has been done so many times. So now let us go ahead and solve for this problem where the whole domain has been discretized with one element. Alright, so the first step, as we all have understood till now, is first we have to define the shape function. So how to define the shape function? So if I look at phi I, how it looks, it is 1 at this point and linearly goes to 0 at this point. So this is node 1, this is node 2. So I have defined like this because the whole domain I have taken as one element. So then what is the definition of phi 1? Can I write phi 1 as, because it has to be 0 at x equal to L. So I am taking it as L minus x, okay, divided by L. Fine, because at x equal to L it is 0 and x equal to 0 it is 1. So that is how we define. So this I will term as phi 1, and so this becomes 1 minus x by L. So similarly phi 2, if I have to define, then it turns out to be x by L. Why? Because at x equal to L phi 2 is 1, so that is what it should be, and at x equal to 0 phi 2 is 0. So once we define phi 1, phi 2, now let us go ahead and calculate the stiffness entries and the force entries. So what are the size? The size of stiffness entry will be 2 by 2 because we have 2 nodes, and each node we have only one unknown, so we have actually two unknowns. So the stiffness entry will be having 2 by 2 size, and F will be of size 2 by 1. Fine. Now let us calculate each of them one by one. So what is K11? K11, uh, uh, we'll just replace I with 1 and J with 1. So in that case, we'll just write EA phi I comma x. As you know, this is basically d phi I dx. So what is d phi I dx? So let me write phi 1 comma x will be minus 1 by L, and phi 2 comma x will be 1 by L. So then phi I comma x, phi j comma x both will be 1 1. So in that case, this becomes minus 1 by L whole square dx, 0 to L. Now if I assume the bar to be uniform, so in that case EA becomes constant. Alright, so then I write this as EA by L square. Alright, and what is integration dx? Obviously this is L, so this gives us EA by L. Fine. Similarly, K12 if I do, what we will get? We will get EA as constant, so let me take it out. So I have 0 to L, phi 1 comma x becomes minus 1 by L, phi 2 comma x becomes 1 by L dx. So that gives us minus EA by L. Fine. Finally, if I look at K22, I am just saving some space, so it will be coming as EA by L. Why? Because then it will be phi 2 comma x square, so in that case it will be exactly same as K11. Alright, so we got the stiffness matrix. Now let us go ahead and calculate the force vector. So if I look at F1, what is the value of F1? F1 is basically Fx phi I dx. So in this case phi 1 dx, and Fx I have assumed as C0. Alright, Fx I have assumed as constant. So it means F1 will be C0 phi 1 dx 0 to L plus what is phi 1. So let us see this part. This part comes from the boundary condition. So if you look at x equal to 0, that is at node 1, so I have basically fixed that end. Alright, so it means that point is fixed, so displacement is 0. So in that case, we always discuss that W vanishes wherever displacement is fixed. So in that case, there is this entry will become 0 at x equal to 0. So only term that will be left out is EA u prime into phi I at x equal to L. So this has been done many a times. So this term at L will give us P naught phi 1 at L, phi 1 at L. But phi 1 at L is 0, so this term vanishes. So what we are having? We are having C naught, and what is C naught is a constant. So the integration phi 1 dx is basically the area of the triangle, and that is basically half into L because the height is 1. So in that case we get C naught L by 2. Fine. So that is what is F1. Similarly, if I calculate F2, what will be F2? Will be the same, because C naught into phi 2 dx integrated from 0 to L plus I will be having P naught phi 1, in this case it will be phi 2 at L. And what is the value of phi 2 at L? The value of phi 2 at L is 1. So that gives us C naught into L by 2, okay, as it is, because C naught is constant, phi 2 dx is basically the area, that is L by 2 plus P naught. because phi 2 at L is 1. Fine. So we got F1, F2, we got K11, K12, K22, Now let us write the full form, because I have, as Raphael told, what is the full form, what is the reduced form, and how to calculate the reaction. So that is the answer I am going to give here with this example. So as you can see, here we will be having EA by L minus EA by L, that is K12. In this case it will be minus EA by L. This part is EA by L. K22 is EA by L. So that is the stiffness entry. We have two unknowns, alpha 1 and alpha 2. Alright. Then here I have F1, F2. F1 is C naught L by 2. This is C naught L by 2 plus P naught. Alright. Fine. So this is the full form. Now after this, what we need to do, I told you that this stiffness matrix is not invertible. So in that case, we have to apply the Dirichlet boundary condition. Okay. So in this case, as I said, here at x equal to 0, my displacement is fixed. So it means that displacement at x equal to 0 is 0. So displacement is defined as alpha 1 phi 1, sorry, alpha 2 phi 2. Alright. And so if u has to be 0 at x equal to 0, then alpha 1 has to be 0, because phi 1 phi 2 are linearly independent. So that is what we discussed. So if alpha 1 has to be 0, how do we implement that? We said that this will take as 1, this entry will make as 0, this will make as 0. Alright, and the right hand term will also make as 0. So this will ensure that alpha 1 is equal to 1. Alright, so now let us go ahead and see what is the reduced thing. So alpha 1 we have ensured as 0. Now how to get alpha 2? Alpha 2 is very easy. Alpha 2, because only we are left with only one equation, that is the second row. So that is alpha 2, we are getting C naught L by 2 plus P naught by EA by L. So that is alpha 2. Alright. Now up to this everything is fine. Now Raphael asked that if I put this alpha 1 alpha 2 back in the full system is this one, that is before enforcing the Dirichlet boundary, then what happens? How do we get the reaction forces? So let us, so because alpha 2 has been calculated from the second row, so if I put alpha 2 back, obviously the second row will be satisfied. But what about the first row? So now let us go ahead and see what about the first row. If I look at the first row, okay, alpha 1 times the K11, that is 0, because alpha 1 is 0. Then I have alpha 2 times the second entry. Okay, so if I write this as left hand side, okay, I am writing this as left hand side because I am just taking this row times this column. So I am getting minus EA by L, so minus EA by L, okay, into alpha 2 C2 L by 2 plus P naught EA by L. Alright, so this two term cancels and the left hand side give us C naught L by 2 plus P naught. So this is the left hand side. Now what about the right hand side? Right hand side gives us C naught L by 2. So I am talking about only the first row, okay, only the first row. So right hand side gives us C naught L by 2. Now what is right hand side minus left hand side? Let's see what is right hand side. Right hand side minus left hand side. So this gives us C naught L by 2. Okay, alright. So here there will be a bracket. Okay, minus of this, so this becomes plus. So C naught L by 2 plus P naught. So that gives us C naught L plus P naught. And what is this? If you look at this, this is basically the total force that is acting on the bar in the right hand side. Alright, so this is basically the reaction at x equal to 0. Alright, so this reaction force is keeping the bar in at equilibrium, and that you can calculate by taking the right hand side minus left hand side, corresponding to the equations that we have already modified in order to implement the Dirichlet boundary condition. Alright, so that's how you cannot put this back and see right hand side equal to left hand side for those equations. Rather, if you take right hand side minus left hand side, you will basically get the reaction forces. Okay, so that is what you need to understand. I think I have addressed the issue of Raphael. So now I will move to the next issue. If you go upside. Yeah, so this is raised by Gokul Basudevan. Okay, so he told that why we are not while calculating the serendipity elements, why we are not subtracting from the corresponding shape function at n1, why we are subtracting from the linear shape function n1. Alright, so let me just address this. So in order to do that, I will take help of that slide that I used to explain it in the lecture. So up, yeah, just one here, 30. Yeah, so here I want to address the issue raised by Gokul Basudevan. Okay, so as I discussed during derivation of the serendipity element, that we will first find out the definition of the shape functions n5, n8 and all. Alright, and then we will subtract some part of it from the linear shape function corresponding to n1. So his question is why this is linear, why not quadratic, for which we are actually calculating. So if you look at the Lagrange shape function n1 for p equal to 2, so let us go ahead and derive the n1. So n1 corresponding to the Lagrange family for p equal to 2 comes from the n1 at xi and n1 at eta. So if I calculate n1 xi for p equal to 2, so n1 xi for p equal to 2, that turns out to be half xi square minus xi. So if you go back few slides, then you will see that I have derived that also. So in that case, n1 xi turns out to be xi square minus xi. And similarly, if I take n1 hat in eta, then that also will be half eta square minus eta. Alright, so now if I take the product of these to derive the shape function for the 2D case, okay, so n1 xi comma eta, then I get 1 by 4 xi square minus xi and eta square minus eta. Now if I tell that this is n1 2, that is p equal to 2, and if I substitute it here in place of linear one, you see that we have a term xi square eta square. Alright, but that is what is the objective of the serendipity element. We need to avoid this term xi square eta square in this set of monomials. Alright, so Pascal's triangle, we said that this is the term that we are going to avoid. So instead of the linear one, if I consider the quadratic one corresponding to the first node, then we'll have this xi square eta square term. Alright, but if I take the linear one, as you can see, the linear one we have only xi into eta, we don't have that quadratic term. Alright, that is how we can actually avoid this term. Alright, so that is why it has been done like that for other shape functions also. I think Gokul, I have addressed your issue. So now let us go ahead and see one more thing. Dharmendra Jain actually raised some question, but I didn't understand. Order of assign the element numbers. I think the question is incomplete, so I will just avoid that. Then Mr. Neeraj Kumar, what will be the type of final test? Okay, I think you wanted to mean the end sem question. So uh, in this case, I'll suggest that you go through the practice sheets. Okay, whatever assignments we are giving, we will not give something away from it. Okay, it will follow the same format that we are giving in the assignments. So I think there is no use of sample question, because that is what is coming in the form of assignments. Niranjana, I have already addressed. Now let us go to the last one. Yeah, here. So regarding 17, in at node 17, why it is 1/4? Because, so let us go to that slide. One more slide, ma'am. Just one more. Just below that. Yeah, this one. Okay, so here as you can see how we choose the coefficient. Okay, we have chosen this coefficient depending on the value of the linear shape function at that point. So if you look at n5, okay, what is the value of n1 at n5? So you have to just plug in the values of xi and eta to find out the value of n1 at that point, and that is what you have to subtract from n1. Okay, similarly at 6, what is the value of n1? That is what we need to calculate. So in this case, the value here is 2/3 and the value here is 1/3. That's why we have subtracted this amount of n5 n6 from n1. Similarly, if you go to the next slide for p equal to 4, okay, so here you just see what is the value of n1 at this point. The value of n1 here is 1/4, because for xi equal to 0, eta equal to 0, if you put it in the definition of n1, I think this is 1/4, 1 minus xi, 1 minus eta. So if you put xi equal to 0, eta equal to 0, you will get n1 as 1/4. So that's why 1/4 of n17 has been subtracted from n1 linear. Okay, so that's how it has been obtained. Fine. Okay, so I will try to address some of these from here also. Okay, can you tell the difference in strong form and weak form? Shivam, I think this I have or we have told multiple times. Say in a given equation, so when we write the weighted residual form, we said that initially that form contains higher order derivatives. Okay, so as a result, whatever the derivative is present in the equation, basically if I have to replace with a set of basis functions, the continuity requirement for the basis function is higher. Okay, say if I look at the bar equation, initially I have second order derivatives, so in that case I have to maintain first derivative continuous. So in that case the shape function should be C1 continuous. Alright, but when we derive the weak form from that, we found that the first derivatives are present in the weak form. So del u del x, del v del x, alright. So in that case, only u should be, or the shape function that represents u should be C0 continuous. Alright, so our continuity requirement has decreased. So that's why that form is called the weak form. Alright. So uh, can you just go up and see a few more? Do we have any advantage to use serendipity element other than minimizing the number of unknowns? Serendipity elements are mainly derived to minimize the number of unknowns. Alright. In fact, in some of the authors have actually discouraged the use of serendipity elements. Okay, instead you can use Lagrange element, but particularly for very large problem. Okay, if you solve a dynamic 3D problem, then in that case you are solving very large number of unknowns. Okay, if you reduce one or two unknowns in each of the elements, then in that case millions of elements you will have, you can reduce the number of unknowns a lot. So in that case you will make use of your resource very judicious. All right. Now super convergent patch test, how to deal if there is point load or material discontinuity. Yeah, so this is a good question actually. The super convergence, so if you have a point load or material discontinuity, so obviously there will be a discontinuity. All right, so in that case we don't need to smooth it out. Okay, there has to be some jump, but when you want to show something visually, okay, so there we can take average of that. Okay, so we can take the surrounding, all the surrounding elements, and we can take derivatives from all the elements at those points, and we can make a average of it. So in that case it will smooth out, and the visualization will be very good. But actually there should be a jump because there is a point load or a material discontinuity. So can you go up? I think few more are there in the beginning. This YouTube. Can I move it? Okay. Fine. Calculated all entries for forces, namely for two elements. For essential moment, can we actually calculate force? I think I have addressed that, Rafael. Gauss numerical integration is not such clear. Will the code be shared? Okay, for the thermal problem, steady state heat conduction problem, I will share the code. Okay, so you can go through the code and match it with the lecture. Okay, so I think that will address your issue. Regarding conducting the online thing, I think a lot of information are there already in the website, so that the MOOCs personnel will tell. I think it is already there. And do we have any? Okay, fine. So I have addressed all the issues. So if you have any query, you send a mail to that Gmail ID. So we'll try to address it as soon as possible. In doc file, anything else? Yeah, I have addressed. So we need to wait for some time. Fine. Hmm? Hmm. Wind up. Okay. Yeah, if you have no more question, then we'll wind up. So if you have any, yeah, could you repeat please why you have C naught L by 2 is equal to 0? Okay, so can you, okay, I have discarded, I think. Yeah, you have discarded. Okay. uh, why you have c naught equal to 0? Yeah, go ahead, you just open one blank slide. Yeah, Rafael, so yeah, so let me just rewrite it, so because we have erased it. So ea by l minus ea by l, sorry, this should be alpha 1, should be alpha 2. The right hand side it is c naught l by 2, here it is c naught l by 2 plus p naught. Yeah, so yeah, because we need to ensure alpha 1 equal to 0. Okay, we need to ensure alpha 1 equal to 0, because u at x equal to 0 is 0. Alright, so now if alpha 1 has to be 0, okay, this is has to be 0, then we are putting this term as 1, this term as 0. Okay, so that makes it alpha 1. But in the right hand side we have a non-zero, is a term which is non-zero, so we have to make it 0, otherwise we will not get alpha 1 equal to 0. Alright, so look at the first equation. If 1 times alpha 1 plus 0 has to be equal to 0, then only alpha 1 equal to 0. So that we always do. Okay, we do not only modify the left hand side, we also modify the right hand side. Alright, so in this case right hand side has to be made 0, because alpha 1 is 0. Alright, if it is non-zero, then we have to put that non-zero value, then only alpha 1, because displacement boundary condition we are enforcing. Okay, we are ensuring that the displacement at that point has to be the value that has been specified. Okay, whereas Neumann boundary condition is not so. Okay, Neumann boundary condition is naturally appearing in the weak form, so that's why Neumann boundary condition is called natural boundary condition, whereas displacement boundary condition is called essential boundary condition. We have to enforce it, so that is why we made the right hand side equal to 0. I think I have addressed your issue now, and I have also told how to calculate the reaction force. I think that is the doubt you are having. Okay. Okay, thank you. So with this I am closing this session. Okay, thank you.